Here is the main page of the university. So you can find the Neptune, the Teams, Moodle, everything here. And starting the Teams because there was someone who wanted to join online, but perhaps, I don't know. Okay, so we will see. Recording is doing, and what I have. Okay, did you check the notes that I uploaded? We're following the Hungarian notes, and I think it's not the best. Not always the best, it's not really mathematics. So finally, we reached this point. Vectorial multiplication, which is very bad, it's vectorial product. I will correct this. I have mentioned it a few times in practice and previously. There are scalar production. You have two vectors, and the vectors production will use a scalar. This is something different. Okay, let's define the right-handed system. Actually, I don't like this term. Very simple. So it's almost not primary school, but secondary. You have three vectors. The first is in this direction. The second is there, and this is the third direction. And this is the right-handed system. It's trying to describe that you are looking from vector C, and then you can turn the vector B to anti-clockwise direction, and this angle is less than the straight angle 180 degree. Yeah, nice. But if you have your hands, then it's easier. If you want to apply it, the first one is this vectorial product of non-zero vectors. You have A, you have B, you have A, you have B, and you have the A carries B in this direction. This is the direction, because there are two important things in the vectors. One is the direction, and the other is the length. And you can calculate the length if you calculate the length of the A and B vector, and multiply with sinus theta, the angle between the A and B vectors. Okay, if you if you do this multiplication with a zero vector, null vector, then the result is a null vector 2. Oh, I forgot something very important. I forgot, and you didn't tell me. We have to write two tests, and the first is oops. No. Oh. I'm lost a little bit in time. This is the third week of this semester. Next, fourth, fifth, 6th, 7th. What is it? You should have classes here, and you don't have. Oh.
If it's like last week of October and first week of November, there won't be any classes.
Yeah, it's. Sorry?
If it's end of October and
Yes.
beginning of November, there won't be any classes.
I know. That's the autumn break. That's good. Holiday. What the hell is this? It's should be here. Okay, that's great when nothing works. Fortunately, okay, no one wants to join. Doesn't matter. I have another other calendar, so it works. This is the third week, 4th, 5th, 6, 7, and we have 13 classes. So, is it okay if we have the test on 17th of October? Your calendar is empty. Okay, so then the test will be then. If you have any trouble, or perhaps I have a trouble, then I can modify this date. Doesn't matter. Okay, and then next week, actually it's quite easy, so we can go to December. So for the second test, 5th of December, that's the last week. And if you have any trouble, then in the examination term, I will provide you time to repeat the tests. Okay. Not okay, but this is what we have. Okay. Yes. Okay. So we have vectorial multiplication. this is not like the scalar product. Vectorial. It's not vectorial multiplication. Why I wrote this? Perhaps I was tired. Do you like LaTeX? Let's see. Okay, much better. So, we have vector product right now, and the features. Yes? Oh, okay. The features. The all other operation that we have was commutative. So if you change the order of the of the product or the operation, you got the same. That was for numbers multiplication. That was for the addition. It was vector addition, scalaric product of vectors. Here it is not commutative. It's anti-commutative. If you go back and see this, you have an A and then a B, you have the A cross B. But if you have a B cross A, then the direction is the opposite. It's also, okay, you can prove this. Okay, doesn't matter. So it's anti-commutative. It is a homogene transformation. So if you have a lambda number and you do the vector product, then you can remove from the brackets from the operation this lambda number. It's quite easy to prove. If you have to give the direction is fine, because if you do the scalar product, you multiply a vector by a scalar, then the direction will be the same, so the direction is okay. And if you look for this, this is the definition for the length, and these are numbers, so you can do this operation. There is one restriction actually that I forgot, but I will write that the lambda should be positive, but doesn't matter. Okay, the vectorial product is dissociative. So if you have a sum here, a polynomial, and do the vectorial product, then you can divide the operation into two parts. And okay, the other definition for, if you have two parallel vectors, then the vector product is 0, because the angle is 0 and the zero angle sinus is 0. So you get a zero length vector. This gives another definition for parallel vectors. If you have two non-zero vectors, A and B. So other definition for two vectors, if you have okay, you have two vectors and these vectors are parallel. If you can find a number that can transform the length from of the first vector to the other. This is it. And this is the sign. Actually, we have defined the what is parallel, what is not. If you have a vector and you calculate the vector product with itself, then it's zero. It's always zero. It's trivial. So the angle between the vector itself is zero. Its sinus is zero, so that should be zero. If you have two vectors and the two vector do the vector product, then and the result is the null vector, then at least one of the vector is a null vector. There is no other way to get a null vector. Okay, remember for this unit vectors, these are normal vectors. Their length is 1. So if you do these calculations, so the A is the E1, then the B is the B, then the A3, the third one is the cross product of the first. And if you go through the coordinate system, you will find this one. So the cross product of the second unit vector and the third unit vector, coordinate vector actually gives the first, and the third and the first cross product gives the second. Yes. Which is very important, and we will use in practice the vector product in components. So that's it. I will not read it. You have vector A, vector B, and the first component is from the second component times from the first vector, second component. We will do examples task for this. It's not so simple. And for example, I don't know it by heart, but it's easy to remember honestly. From the unit vectors, you can easily memorize it. Okay, so the A cross B vector product is a way to calculate a parallelogram. So this is the gives the area of the parallelogram. It's easy to prove. This is the basis of the parallelogram, and with the sinus of this is the height of the parallelogram. Okay, this is useful when we do some exercise. Okay. Now the things will be a bit confusing, because now if you check the notes, I will do something else. First of all, we should we have to give the definition of the triple product. It's a mixed product. So if you have vectors A, B, and C, and you calculate the vector product of A and B, and then multiply by scalar product with C, that's the triple product. The Hungarian term is mixed product, but triple product is the right term. And similar to this, if A, B, C is a right-handed system, then ABC is the volume of the parallelepiped of the ABC vectors. If it's not a right-handed system, then the number is minus 1 times of the volume. And remember, for these equations, in this order, you always get the same number. Okay. We should define what is determinant, what is matrix, but in the notes, well, I don't like what they do. If we are in a university, then we don't do only just calculations and everything. We have to explain everything. I don't know whether it helps or not, but I try to explain in particular what we do. At least give a sketch. Let's go back. You should have learned this. So what are sets? You have other mathematical courses, don't you? So what is a set?
A group of elements.
Yeah, but what is element?
Can be anything, including alphabets and digits.
Yeah, but what is the definition of element? No, it's okay. That's the right answer.
Are just things. Like, it could be numbers, it could be objects, it could be anything, it could be even
I understand this. That's okay. Just there is no definition for the element itself. So it's things. So this is something fundamental term,
Yes.
and there is no appropriate definition. If you are a mathematical physician, or your specialization, you are a mathematician, and you are your special interesting field is the sets, then you can give some terms. You must have a statement, and based on this statement, you could decide whether something is part of the set or not. So if I said, for example, people with blue eyes, that's not good, because what is blue? For example, do I have green or blue eyes? It's not good. But if I said, for example, I don't know, right shoe and left shoe, that forms a set. This is okay. This is not the most important thing of the life and mathematics. Just you have a set. Okay, what is pair? Pair is just sets with two elements. That's quite simple. What is ordered pair? That's more important. You have to give somehow the direction. So if you have a pair consists of A and B, is not the same like B and A. And this is the definition. You have a set, the first element. So you have this pair, and it means you have a set, and the second part of this pair is part of a set, and this forms a set. This is an ordered pair. And now the things are much more difficult. You have calculus. You should have elementary analysis, function analysis, or something like that. This. Do you have this?
Function analysis?
Function analysis, yes.
As if how functional rise, increase, decrease were positive and negative?
Excuse me?
Where we concluded function increase, decrease is positive or negative?
Yeah, yes, but you should have a similar definition at the beginning.
In my previous studies we did, because I was
No, okay, your previous studies does not exist for the others. So please, do you know what is it? I tried to explain what is a function and what is a relation.
Function is the relationship between output and input, like the certain value of input has a proper and unique output. Certain value of input has unique output.
I think we are talking the same. Do you have relations? Do you need relations previously?
Relations, direct relations. And
No, this one. So there are more general terms than functions for operations and everything. No, doesn't matter. I just try to explain. So if you have a set of ordered pairs, that's a relation. At least how I learned it. The relations have, so for example, here, this 1B, 2C, 3D, these are pairs, and this is a relation. It should be something like this is a relation. Some of them is injective. Do you know what is injection, injective relation?
When we have one-to-one correspondence. When we have one-to-one.
Yes, that's it. So this is what that I try to write here. This is an injection. Different elements are ordered to different elements. That's the injection. If you go through further, there are surreactions. The surreactions is that when you this is one set, this is another set, and you order all of these sets. You order to all of these sets something, but it could be multiple. If something is an injection and a surreaction, then then you have a reaction, and you ordered all elements of this set to the other elements. Okay. From these relations, there are a special thing called functions. So it means you have, oh, the bracket is, sorry, this is bad. Just a moment. Great, that's better. So you have three elements, and this relation and this relation, if they are fulfilled, then this so these elements should be the same. This function is the same that you learn in Descartes coordinate system. Just it's better if you give an exact definition for this. And now something is more difficult. Linear relation. Vector spaces are nothing more, just a set of vectors. And we have two vector spaces, actually vectors. There is a body, you will learn what is body later, just consider it's a scalar number. This relation, this F relation is linear if it's additive. You have two elements from this vector space, and you apply the function, and you can divide it into two functions in this way. You have seen this a few times previously. Then it's homogeneous. It means you have one vector, you have a scalar, for example, and if you have this multiplication, then you can remove the lambda before the function. This means linear. This is a very general term. I told you many times that I talked about perpendicular things or orthogonal things, so these have a very general description, definition. Okay, and now I can tell you what is an operator. The operator are linear vector-vector functions. Okay. This is a short definition. Just I have to define what is function and what is linear. Nothing of any of them is trivial. You feel something. You have a vector here. Now it's better if it's x. And there is another vector here. Somehow you can transform one vector to the other. One vector to the other, but how? If you multiply this calculated product with a scalar, then you change the length. You somehow should modify the coordinates, and that's much more difficult than you imagine. And this is the material, the rest of the semester actually. This function is something special. It's a vector function. From this vector you got this function. In the real life, for example, in physics, it's you describe, for example, the tension if a solid material in this, or if you have perpendicular moment. So these are operators, and that is because there are vector functions, and we need a restriction. They should be linear. In nature, we really like linear things. If it's not linear, then that's horrible. Usually, we cannot do anything. For example, the weather, the climate, nothing is linear. It's non-linear. And if you have a small perturbation or anything, then you have one result with some measurements. And if you have a very small deviation from it, then in a linear system, the result is deviates, but you can see how deviates. But if the system is non-linear, then if there is a small deviation at the starting points and measurements, then the result could be anywhere. So we do restriction, and mostly we deal with linear things. Actually, not really, but in the last decades we started to discover and chaos and fractals and other things. But usually we have sharp edges, points, spheres, cubic stuff, and linear stuff, because otherwise the mathematics fails. Actually, not the mathematics fails. We fails to fix the equations and the models. So operators are linear vector functions. Very simple. What is an identical operator? If you multiply any operator with it, then you got the same operator. You also have a null operator, and if you multiply anything with that, you got that operator. Here you should be very careful, because I calculated the products on the right, but you also can calculate the products from the left, and the result is not the same. Now these are very weird objects. We had scalars, we had vectors, now we have operators. These are weird objects. The scalars are scalars, that's fine. The operators are a bit more difficult. There are mirror operators. You have an x vector, then you got minus x vector. You can do it with an operator. That's mirror operator. Sorry. If you have an x vector and you apply so-called projective operator, then in any time when you apply it, then you got the same. And this is the projector. Now it's something weird object, but you will understand why is it important very quickly. You have two vectors, and you can rotate them, which is important for these rotation operators. It does not change the length of the vector. But I will not tell you more about this right now. And now, at last, okay, that was the third condition criteria. Wrong lecture, doesn't matter. So this is the material of the one of the most important part of the semester. We have scalars, that's okay. We have vectors, and the vectors have representatives in coordinate systems. Now we have operators. These operators also have representation in coordinate system with numbers. That's table it is. Very nice. But absolutely not understandable. I have an x vector 0, 1, 0, 0. Now I have a matrix you have to write much more. This is the representation of an operator. That is a linear vector function. So you have, actually, in this definition, you have a real number. You have two non-negative and non-zero number. It's m and n. And then you have this table. Here the m and the n is 3 and 3, so it's a cubic matrix. That's quite simple stuff. So you have numbers here, and this is the definition. But this is not that. this is not cubic. So the columns, the rows, the number of columns and the number of rows are different. It's a bit more difficult to do operations with it, but you will learn how to do it very soon, sooner than you expected. The spur of the matrix. Okay, first of all, you have if you have a cubic matrix, then you could have a spur, and that's it. So the indexes with the same number 1, 1, 2, 2, 3, 3. Okay, sorry, I forgot to explain, but that's quite simple. No, it's if you have an element, it's alpha Eig, then the index of row is the I, and the second index is the column G. Okay. And this is the spur. So, if you want to multiply this, if you do the product, then you multiply this number with this number and add this number with this number, and it's quite simple in this case, and this number and this number. Then multiply this number with this number, then multiply this number and this number, and multiply this number and this number. This is here, this number and this number are multiplied, and this number and this number multiplied, and this. It means it's 1, 0, 0, it's 0, 0, 0, 0, 0, 0. Okay? It's not simple. If someone has learned it, then it's simple. If not, then it's not simple. I will give you a lot of tasks to multiply these two numbers. This is very simple, and if I change this x vector, okay, this is multiplied, and then 0 times 2 plus 0 times 3, 0. Okay, 0 times 1, times 2 plus 0 times 3, then 0 times 1, then 0 times 2, then 1 times 3, it's 1, 2, 3, because this is the unit or ID operator. In the spool, there are only one. You have this matrix. When you do this operation, multiply a vector with a matrix, apply the vector function in representation to the vector, then you multiply each element of the row with the column of the vector, and then add together. This is what I had done a few times. Okay, the life is not always easy. The life is not always a chocolate cake. Have you seen The Witness? It's a Hungarian movie. Did you have any cultural briefing? Doesn't matter. There are some sarcastic terms like Hungarian orange, it looks like lemon. Doesn't matter, you will see. So, I give you another operator, and that's not easy. I have, actually, I made my life easier. This is not like that one. This is a cubic, so the number of rows and columns are different. If you want to multiply this with a vector, you cannot do it with all type of vectors. You need a special one. You need, and you can do the operation if the element of the vectors has the same element number like the column number of the matrix. So this A times X is nothing more than 1 times 1 plus 2 times 2 plus 3 times 1, and then here here 1 times 1 plus 0 times 2 plus 1 times 1. It means 1, 5, 3, it's 8. 1, 0, 1, 2. So you got this. This is a different operation. You will have homework. We will practice this tomorrow. Don't worry. I have in A matrix an A operator. I also have a B. And I can have operation with them. For example, A operator times B operator, plus B operator is nothing more than adding the elements. You just add the elements, nothing else.
Can we also multiply them?
Sorry?
Can we also multiply them?
Yes, that will be the last one. And you can do a lot of other things with them. It helps to fix linear equations, system of linear equations actually, and a lot of other things. You also can calculate A minus B. It's quite simple. 1 minus 1, 0 minus 0, 1 minus 0, 0 minus 0, 2 minus 2. That will be an interesting result, I think. 2 minus 2, 0 minus 0. And finally, 1 minus 0, 0 minus 0, and 1 minus 3. And that is 0, 0, 1, 0, 0, 0, Jesus Christ. 1, 0, minus 2. Ow. It's sometimes painful to write. So these are the two okay, and now we can multiply this, and that's not easy. If you want to multiply, then you have to calculate the following stuff. You take these numbers and these numbers, and each pairs are multiplied and summed together. You will see very soon. It's 1 times 1 plus 0 times 0 plus 1 times 0. This was one element, only one from the 9. So the next one is 0 times 0, 0 times 2, 1 times 0. So okay. Then this one, this one, this one, this one, this one, this one. I also can see it's 1 times 0, 0 times 0, and 1 times 3. And now we have the first row, second row. This times this time, and this, and this, this, and this. 0 times 1 plus 2 times 0 plus 0 times 0. Okay. 4 from 9. Next one. This and this. This and this. And this and this. It's, if I remember, it's 0 times 0 plus 2 times 2 plus 0 times 0. I'm right? Yes, great. And then this and this, this and this, this and this. It's 0 times 0 plus 2 times 0 plus 0 times 0. 0 times 3. Thanks. That was, yeah, that's one. Okay. Last one. This one, this one, this one, this one, this one, this one. So it's 1 times 1 plus where we are. Yeah, 1, no, 1. Okay, I lost. That's, no, please. 1 times 1, 0 times 0, plus 1 times 0. Next one. Okay, then you know actually, so it's great. Where we are. So it's last and this one. This one, this one, this one. Means sorry. No. Okay, and the last one. This one, and this one. Means 0, 0, and 3. Great. Now we just have to do the calculation. By all cost. And what is it? So it's no, it's 1, then 0, then 3, thanks, 0, 4, 0, 1, 0, and then 3. So this is the result of the calculation. Not easy. This is a good opportunity to spend your time. Yes. Okay. There is one number, a very important number, that is related to matrices. I will give an exact definition later. Called determinant. And there are two ways, at least for 3 times 3 matrices to calculate. One, that's the most difficult. No, I just show you the simplest. You multiply these and these numbers, and then subtract these numbers. Okay, it's not easy. It's 1 times 1 times 1 plus 0 times 0 times 1 plus 1 times 0 times 0. That's, minus 1. Oh, sorry, that's something is wrong. 1 times 1, 0, 0, 1, and then 0, 0, 1. Okay? And the other is 1 times 1 times 1 minus 0 times 0 times 1 minus 0 times 0 times 1. And that is 1, yes, minus 1, 0. The triple product is the same like this determinant, and I will show you a lot of things that related to these operators, matrices, and determinants, but not now. I think the time is over. So thank you very much. I will upload everything on the Teams and Moodle. Do you prefer Moodle or Teams? Teams? Really? Really? Why?
Other professors use only Teams. Yeah.
But what they do actually with the Teams, because I'm not very familiar with Teams and use Teams.
Documents.
Yes, that's okay. And what else? Because in Moodle you can write tests, you can give the tasks, exercises, homework, and everything.
In Teams there's just test section.
I also
Yeah, but we didn't do it. No one like sent me test.
So no one checks Moodle?
Actually, like only for our dormitory training we use Moodle.
What is on training?
Higher training.
Fire training. Okay, thank you. Thank you. Well, great. Yes.
I have one question.
Just a moment. Okay, just a moment. I switch off the recording. Okay, I'm just